Hello everyone. This is EE698G. We are at lecture 4. And in the last few classes, we have been looking at a circuit called as delay locked loop. So this basically is going to take an input, or which is usually a clock signal. This clock signal is then passed through a variable delay line, which is a voltage controlled delay line. And then we take the delayed versions of this clock and compare it to the clock waveform itself. So we first detect the phase difference. And based on that, we are going to push or pull charges from a capacitor. This will develop a steady state voltage across this. And the steady state voltage is going to be used to control the voltage control delay line. Now, in the last class, we saw two main architectures of the voltage control delay line. So one was to tune the charging or the discharging current, and the other method was to tune the capacitance. Okay, so what was common in both these methods was that we are trying to change the slope of the waveform. So let me explain. So let's say I had an incoming rising edge. We will assume a buffer which is introducing a delay. So what we were trying to do was to change this slope of this waveform at the rising edge. For example, let's assume that this is at t equal to 0. That is, we have this rising edge at t equal to 0. At the output, we were going to see waveforms with different slopes like this. So this is my first waveform. Now, if I increase the capacitance or reduce the current, I would have another waveform like this, right? If I increase it further, this is my third waveform. And I could have a fourth waveform, etc. Now, if our point of reference is 50% of the output, which is usually the case, then you see that for each of these waveforms, I get a different delay. So if this is my T1 and this is my T4, you can see that T1 is much, much smaller than T4. Basically, sharper the rising edge or higher the slope, I have a smaller delay, right? So this method of varying the slope to get a variable delay is called as variable slope method. Okay, and the two methods that we discussed so far falls into this category. Now, the other method is called as constant slope method. Now here, again, let me assume that this is my input waveform. Now to introduce the delay, I'm going to change the starting point of the slope. So for example, let's say this is one delay waveform, one output waveform. Now instead of starting from V equal to 0, let's say I start from a slightly larger point. So some V equal to V1. And I retain the same slope. So then the waveform will look like this. If I start at a slightly larger point, this waveform will look like this, right? So now basically, if I again consider this 50% as my threshold point, you will see that all of them will have different delay. So this is my T1 and this is my T3, right? So now this is obtained by making sure that your signal is not starting from ground, but from a different voltage. Now this method has a potential to give you very linear characteristics for delay versus control node voltage. In the earlier method, if you remember, the waveforms you got were not linear, right? It did not have the same slope throughout. However, this method has the potential to do that, provided we limit this variation of VC within a particular value here. And this particular value is usually smaller than the threshold voltage of the inverter. Okay. Now, we will not cover this method in detail in this course, but I highly recommend reading the paper in which this method was first discussed in. So let me show you that. So this is that paper. This was published in 2015, and this was published in IEEE Journal of Solid State Circuits. So I have opened the full paper here. So again, this is one of the reputed journals. Journal of Solid State Circuits, or JSCC, is one of the reputed journals for people like us who work in IC design. And it's a name that you can look out for. And I highly recommend reading at least the introduction of this paper. This is a beautifully written paper, and how they explain the concepts is also very nice. Okay. All right. So with that, we come to the conclusion of the discussion of our voltage control delay line. I want to discuss one more portion on this, that is the tuning range of the delay line. Okay. So let's say we have a characteristic like this. So the x-axis is VC, y-axis is the propagation delay, and let's say I have some characteristic like this. Now, usually you can vary your VC, let's say from 0 to VDD, right? Then the corresponding tuning range is here. So this will give you some delay range across which this variable delay line is tunable. Now, in a lot of cases, the moment you put this in the feedback loop, you will have some limitations on how much the VC can vary. It could be limited to a smaller range, let's say from V1 to V2. Right? So then the tuning range that you have now is smaller, and it will be this. So let me call this as some T1, and then now the tuning range is smaller, it's some T2. Now, if the clock of interest is some T clock, and ideally we are trying to lock this delay line to one clock period, that means your corresponding control node voltage will be a value like this. So you have to make sure that the locking point that you want, in our case it is one clock period, should lie on this curve. Okay. Now let's see how this theory can change a little in the presence of process voltage and temperature variations. So let's say I again have VC, and I'm going to set the range of VC to some V1 to V2, right? Now let's say in the fastest corner, my delay line has a curve like this. Okay, so what do I mean by fastest corner? Of process voltage and temperature are such that you have the minimum delay. So this means that now your transistors are in fast corner. So you have both NMOS and PMOS in FF. Your supply voltage is 10% higher than the nominal value. So you have, if your nominal value is VDD, you'll have 1.1 VDD. And your temperature is the lowest temperature for which you have to design your circuit for, right? Now, let's say the next curve is the typical or the nominal behavior, which means the corners is typical. Both NMOS and PMOS are in typical corner. You have VDD, and your temperature is the room temperature or the ambient temperature that you expect. And finally, we will have the slow corner, where the process is SS, both NMOS, PMOS in slow corner. Your supply voltage is a lower supply voltage, and you are simulating for the highest possible temperature, right? So now, as you go from fast to the typical, your curve is going to shift like this, right? Now, if you simulate for the slowest possible corner, it is going to look like this, right? Now, let's say this was my first clock, T clock 1. And let's say I had another clock, T clock 2. Can you comment on whether I can lock this delay line to T clock 1 or T clock 2? Right. So if I had T clock 1, you see that this is the only possible solution. So only if your chip is operating in this condition, you will have a locked solution. You will be able to lock to T clock 1, which means you either have to redesign this to be able to lock to T clock 1, or you shouldn't have T clock 1 as one of the locking points. You need to use a different clock period as a whole. Is this clear? Okay. So now if I look at this curve, right, you see that these two are not touching at all, right? Which means I don't actually have a solution for this problem. So I will anyways have to redesign it. So you figure out how to redesign it such that you have at least some common range. So now it looks like you can lock to any clock period within this region. Okay, this is clear? Right. So typically you will have to over design at some corner so that your chip is working at all the corners. For example, if I look at the first corner, it's clearly an over design, right? You are targeting for clock periods much smaller than what is required, but that over designing is required so that your chip is able to meet the specs in all corners. Generally, this is the case. This is okay? Okay, good. So now let's get back to the delay lock loop again. Now we said that for detecting delta phi, we will be using a circuit called as, do you remember the name? Phase detector? Yeah. So as you can see, none of these names are complicated. So now we are going to look at the phase detector. And instead of looking at the phase detector that is just most suitable for the delay lock loop, we will take a broader approach and we will look at a lot of phase detector topologies. Okay, and then we'll pick the one that is most suitable for this delay lock loop architecture. So let's start. Okay, so what does the phase detector do? Let's say I have two signals, in 1 and in 2, with some phase error between them. My phase detector has to give an output that is a function of this phase error, right? So I can have a phase detector, which I'll now abbreviate as PD. So this is my in1, this is my in2. They have a phase difference of phi error between them. And then it is going to give an output VPD. So V, because it's usually a voltage signal, PD for phase detector, right? So we want our VPD to be a function of phase error. Now it turns out in most of the implementations, instead of this VPD being a function of the phase error, we look at VPD average as being related to phase error. Okay, so we'll get some VPD waveform. We'll then take the average and we'll see that its average is what is related to the phase error. Right? Now let me also define this phase error very cleanly. So this phase error is basically the difference between the total phase of the first signal minus the total phase of the second signal. Now, in all our discussions on delay lock loop, both the waveforms will have the same frequency. Okay. So now let me say for this particular case, let's say in2 is lagging in1 by an amount delta t. And let me also represent my in1 of t as some function into gamma omega naught t. I'm assuming that it doesn't have any initial phase. How can I write my in2? What is my in2? Can you tell me? Nothing was clear again. So it will be gamma into omega naught t minus omega naught delta t. Is this clear? So can you tell me what the phase error is in this case? Is it plus or minus? That's what I want to know. Why is it minus? Let's write the step. So this is phi1 of t, which is omega naught t, minus, I have to do phi2 of t, right? So this is omega naught t minus omega naught delta t. So can you tell me the answer now? This is simply omega naught into delta t. Clear? So this is 2 pi by t naught into delta t. Okay. So our definition of phase error is such that we are going to subtract the total phase of phi2 from phi1. If I have two inputs in one and into, this is how we are going to calculate. So if into is lagging in one, we will have a positive phase error. Okay. So now we can classify the phase detectors broadly into two categories. The phase detector could have an analog implementation, or it could have a digital implementation. So now within this analog implementation, we are going to look at multipliers. So multiplier based PD, and we will look at sample and hold based PD. So here in digital implementation, we will look at XOR based PD, then the SR latch based PD, and finally we will look at what is called as phase frequency detector. Okay. So now let's start with the analog. So let's start with the multiplier based PD. So can you guess what it is going to do based on the name? Multiply two signals. So I have in1 of t, and I'll multiply this with in2 of t, and I'll get some output VPD. Okay. So now multiplier based PD is generally useful when both the inputs are either sinusoidal or cosine waveforms. So let me assume in1 of t to be some a1 into sine of omega naught t plus phi1, and in2 of t is some a2 sine of omega naught t plus phi2. Okay, so I am taking both sine waves to be of the same sign, because in our case, we are anyways going to delay it and then compare. So there will be no difference in the frequency, right? So can you tell me what is VPD? Please solve. Okay, so now if I take the average of this VPD, what do I get? So we'll get A1, A2 by 2 into cos of phi1 minus phi2. This high frequency term is going to get averaged out, right? So what is phi1 minus phi2 now? This is our phase error. So we get a relationship like this. Okay. So now we can plot the characteristics of this phase detector. So x-axis is phase error. This is in radians. Y-axis is going to be the average of the VPD. So can you plot this waveform? Okay. So now looking at it, let's say we are operating within the range of 0 to pi of phase error. Where do you think will be the locking point? So I have put this phase detector in my delay lock loop, right? So where do you think, if I put this phase detector in my delay lock loop, where do you think the loop will lock? To phase error of 0? VPD has to be 0, right? The output of the phase detector has to be 0. That will be the locking point, right? So you're detecting something and you're generating an output. So if that output is 0, that is when the rest of the loop is not responding, right? Right. So our output of this phase error has to be 0, which means we have to be here, right? So this, because this is now locking with a phase of pi by 2, this is also called as a quadrature phase detector. Okay. So now, can you tell me, okay, before I do that, let's say we have already locked to this point and there is some minor change in the phase error, right? Let's say the phase error became slightly lower than pi by 2, which means we are now here on the curve. So we have a relationship that when the phase error is decreasing, my VPD average is increasing, and we will configure the rest of the loop such that when your phase error, for this relationship between VPD and phase error, you have a negative feedback. Okay. So now this brings me to the next point, which is the requirement of having a monotonic curve. So do you know what is meant by monotonic curve, etc.? So let me quickly give you an example. Okay. So this is a monotonic curve. This is also a monotonic curve, right? But if I draw something like this is not monotonic. Neither is this. Okay. So now can you tell me what is monotonic? So this is strictly increasing or strictly decreasing. It shouldn't increase for some time and then change sides and start decreasing, right? Or in other words, if I were to look at the slope of the curve, it is either strictly positive throughout or it is strictly negative throughout. Okay. And this behavior is very important. For example, so let me extend this curve slightly to the side. So as you can imagine, we have the exact relationship. You can plot it for any value of phase, right? So now due to some reason, if from this ideal locking point, let's say it gets shifted beyond pi, right? So now the relationship between phase error and the VPD average has changed, which means the loop can enter into a positive feedback from being a negative feedback originally. So this is why when you have anything in the loop, you have to either make sure that it is monotonic throughout, or you identify a region where it is monotonic and limit your operation within that region. Right? For example, in this particular characteristic, I could either operate between 0 to pi. Between 0 to pi, it is monotonic, or I can operate between minus pi to 0. Right? So let's take the range from 0 to pi. This curve is now monotonic in nature. And the range where this curve is monotonic is roughly pi, right? It could be either from 0 to pi or from minus pi to 0, but your phase error cannot exceed beyond this value, right? So the range is pi. And can you tell me if it is linear or not in this range? This is not linear. So you have a monotonic curve, but it is not linear. which is okay. We can live with a nonlinear curve. We'll just do small signal analysis and linearize it around a particular bias point. That's it. Okay. So now we have to define a gain for the phase detector, right? So this gain, again, represented using KPD, is defined as follows. So you look at by how much your phase detector output is changing when you have an incremental change at the input. So basically, this is change in VPD average when you have an incremental change at the input. Or in other words, I can write it in form of derivative of VPD average. Or this is same as the slope of the VPD average versus phase error curve. So you have the expression. Can you calculate what KPD is for this? So you have the expression for VPD average. What is the expression for KPD? So what is the exact value? Minus A1, A2 by 2 sine of phase error. Okay. So again, plot KPD versus phase error. So if again, we are limiting our operation region to 0 to pi, which would mean that we are in this region where the KPD is negative throughout, because we want the slope to be negative throughout. And you'll also see that the maximum gain is around our locking point pi by 2, which is usually a good thing. Okay. So I know we did a lot of math, but does it make intuitive sense that when you have two sinusoids or two cosine waveforms, the locking point is when they are at quadrature phase between themselves? We saw a lot from the math, but it shouldn't be like, we say, yeah, it comes out of the math. We should have some feel for it. So if this is my first sine wave, multiplication is? So you're multiplying and then taking the average. So I'll plot something with same phase. So if I multiply and take the average, if I multiply, how would the waveform look like? So it will basically a rectified version, right? So it will look like this. Then I would have the average somewhere here, right? Now, if they were 180-degree phase shifted, I would have the whole thing on the negative side. Then the average would be some negative value. Now, if they are 90-degree phase shifted, you'll see that it will exactly cancel out each other. Okay? That makes sense? Okay. Right. So now let's move on to the second phase detector. So this is a sample and hold based phase detector. So this is generally useful when one waveform is sinusoidal And the other waveform is a square or a rectangular waveform. So this is my input 1. And now I'm going to draw my into to be a slightly delayed signal. And I have a delta t here. Okay. So what we are going to do is we are going to sample in one at the edges of into. So we will have these voltages. I didn't draw it exactly equal. All right. So just by looking at it, so now these voltages are going to be my VPD value. So just by looking at it, can you guess as to what should be the locking point? Zero phase error. So what he's saying is, if the rising edges were happening exactly at these points, then my sampled values will be 0, right? So then my VPD will also be 0. Okay. So let's see if that comes out of the maths. So I'm going to call my in1 as some sine waveform, sine of omega naught t. Let's say my in2, which now it's a square wave, so I'll simply represent it as some gamma of omega naught t minus omega naught t delta t. Okay. So now my VPD will be samples of in1, right? At what point am I sampling? So let's look at it. If this is delta t, right? What point am I getting the first sample? At time equal to t equal to delta t, right? So this is t equal to something. I'll write the full expression in a minute. Let's say this is time period t naught. So what time point am I getting the second sample? T naught plus delta t. So effectively, I will be sampling at n t naught plus delta t, where n can go from 0, 1, 2, etc. So this is a generalized expression. Okay. So now let's put this information into in1. So my VPD is basically sine of omega naught into, instead of t, I have to write it as n t naught plus delta t. So this gives us sine of n omega naught t naught plus omega naught into delta t. Any questions here? This is clear? Okay. So this is equal to sine of 2 pi n, because omega naught and t naught will get cancelled and you get a 2 pi out of it, right? So 2 pi n plus, what is this quantity? That is my phase error. Okay. This is same as sine of phase error. Okay. So now what is VPD average? Same signal, right? Sine of phase error. Did you guys say 0? Why did you say 0? You said 0, right? Huh. Okay. So when you finally look at it, right, your VPD waveform is going to be samples, which is sampled and held. So you will hold the sample also for till the next cycle. So if phase error is constant, you will get a constant output. Okay. So now again, please plot VPD average versus VC, versus phase error and its gain as well. So you got the characteristic like this. Now, can you tell me what the locking point is? 0, which is what we saw intuitively in the beginning as well, right? Okay. Now, what is the monotonic region that you can use? So we can operate between minus pi by 2 to plus pi by 2. Now, this region is monotonic. So from minus pi by 2 to plus pi by 2, which means you now have a range of pi, which is same as the multiplier based PD. Is it linear? This is not linear. All right. And what is the expression for KPD? It should be plus cos of phase error. Okay. Again, you can plot the KPD as well. All right. So now let's move on to the digital implementations of phase detector. We'll start with the XOR based PD. So generally, when we say digital PD, all that it means is that the inputs in 1 and in 2 are either square or rectangular waveforms, and we are using logical gates to implement the PD. Okay. So here we are going to use an XOR. This is my in1, in2, then I have VPD. Okay. So quickly tell me the truth table for an XOR. 0, 0. Yeah. 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. So I'll give you an in1 and in2 waveform to plot. You can plot the VPD. So our VPD will look like this. Okay. So this pulse width now has the information that we require. This is delta t, right? Now, if this signal had a period of t naught, what is the period of VPD? It will be t naught by 2. So can you write the expression for the average value of VPD? So I'm looking at the average of the signal. Let's say this is switching between 0 to VDD. So I'm connecting the supply like this. VDD into divided by T naught by 2. Can you give an expression in terms of the phase error? Right, to take the average, I find out the area under this curve. So that is delta T into VDD divided by the period T naught by 2. This is holding true because we are switching from 0 to VDD, right? So then I can write it as 2 into delta T by T naught into VDD. So what is delta T by T naught? That will be phase error by 2 pi, right? So 2 and 2 will get cancelled and I will have phase error by pi into VDD. So I can write it as VDD by pi into phase error, Everyone got this expression? Okay, now tell me, looking at this expression, so I have VPD average and I have a relationship with respect to phase error. Is this linear or non-linear? This is linear. It's actually quite surprising, right? We started off with an XOR, which is a non-linear block, right? It doesn't respond to minor changes in the input. It gives you either 0 or 1 as the output. So it's very non-linear. And using a non-linear block, with our definition, we are able to get a linear relationship, right? Is it clear? So even though we are operating with a non-linear block, our VPD average is linear to phase error. Okay. So now before I plot these characteristics, I actually want you to plot this for phase error equal to pi, for phase error between pi and 2 pi, and for phase error between minus pi and 0. I'll tell you the reason why we are checking for these three conditions. So if I were plotting VPD average versus phase error, this equation that we got, can you comment on for what range of phase error it is going to hold? Looking at this. So anyways, for phase error greater than positive and phase error less than pi, it is holding. 0 to? It will hold for delta t equal to 0. For delta t greater than 0 also it is holding, right, to some extent. So can you, looking at this waveform, can you comment on whether it will hold for 2 pi, whether it will hold for pi by 2, etc.? It will hold till pi by 2 for sure, right? Right. So let me draw till pi by 2. And at pi by 2, what is the value? VDD by 2. So now I want to get a whole plot till 2 pi. So here I have pi and 2 pi. And here also I want the plot till minus 2 pi. Okay. So can you do the timing waveform for these three scenarios? You don't have to give me the exact expression. Do the timing waveform and see how this plot is going to look like. Right? We know that the relationship is going to be linear. Make use of that fact. And can you do the timing waveforms for these three cases and see if you can fill in the rest of the characteristics. So now our waveform is, our characteristic is like this. This value is at VDD. And then for 2 pi, it again falls back. Similarly, you get the similar characteristic on this side. Assume that I have drawn it symmetrically for now. Okay, good. So now tell me, what is my locking point? Patience. Okay, let's take the answer that this is my locking point. Okay, the reason why you said that is because the VPD average is 0. So now I again ask you, is this a good locking point? Yeah. So let's say you lock here, right? And let's say you configured your circuit such that if the gain is positive, you get negative feedback. But you are locked to this edge. So even with slight noise in your circuit, your point might shift to this side, right? Which means this ideally shouldn't be used as a locking point. You should be at the center of a monotonic region, right? So if I look at the monotonic range, this is from 0 to pi. or I could say from minus pi to 0, right? So then ideally, I would like to be positioned at the center of the region, which is here. So at phase error equal to pi by 2. But then this current curve cannot be used as it is. We have to do something to shift this curve downwards, right? So this change can be done either in the XOR or immediately after the XOR. But all that you have to do is now shift the curve downwards such that for value of pi by 2, you cross through the 0. So this value will be equal to VDD by 2. This will be equal to minus VDD by 2. So we'll not worry about how to do this currently, but like I said, it can be done quite easily by making either some changes in the XOR gate or immediately after that. Okay, so now whenever we discuss about XOR PD, it is with the understanding that it can be used only after shifting the characteristics like I showed. Okay, so now if I consider the range from 0 to pi, this is monotonic. Is it linear? This is also linear, right? And the range where it is monotonic is equal to pi. So not much improvement here. This is same as the other phase detectors we discussed, but at least this is linear in nature. And also logical gates are much more easier to implement. So that way there are more advantages to this phase detector. Okay. So now here is one question that you can try out. So this is a homework. You can try it out later. So plot VPD average versus phase error when both inputs have pulse width equal to T0 by 4 for an XOR based PD. Here we have assumed a pulse width of 50% in our discussion. So now the pulse width is T0 by 4, which means it is much lower than its 25% duty cycle. So this is something for you to try. I will also give one more homework. So I still have my XOR PD, but instead of connecting in1 and in2 directly to the PD, I will connect it at the output of a divide by 2. So I have in2 coming here. This flop is configured such that its output is the divided down signal of in2, right? So I do the same thing here as well. This is in1, and this is equal to VPD. So repeat 4.1 for this circuit. Okay, so now let me give you one exercise to do right now. So we are going to assume that in1 and in2 have different duty cycles. Okay, let's say in1 is at 50% duty cycle. In2 has less than 50% duty cycle. You have to plot VPD average versus phase error for XOR based PD. Can you quickly try that? You can look at the characteristics between 0 to 2 pi. That might be easier. So we'll start with an N1. And let's say I have an N2. So I'm going to start with both of them having the same phase, with N2 having a smaller duty cycle. So the VPD is going to look like this. I started with the same phase error. So it is zero phase error. And then here I will have a pulse like this. Then it is 0. Then I will have a pulse like this. This is fine, right? So what this immediately tells you is, even when the phase error is 0, the output is not 0, because there is some average now, right? Now let's say I delayed my N2 slightly. Okay. So what is happening now is I will have a small pulse here, right? And this pulse is also going to reduce. But if I look at it, the area under this pulse will be same as the area that has reduced here, which means the total area now is same as the total area earlier. So my VPD average is still not changing. Correct? And this will continue till my pulse has moved out of this region. Okay. So if I look at the original curve, you'll see that you have a non-zero value. And after some point, it will start following the curve. And then you'll again have this you'll again have a shorter value. It will not reach till VDD. And then it will continue. Okay. Now, is this behavior okay? Is it okay to have a flat region here? It is staying monotonic, but is it okay? So, okay. It will be much, much slower, right? It's as if the loop is not responding to the changes happening in the circuit. So if I were to look at the gain curve for this, so our original gain curve, let's say I am plotting KPD versus VC, versus phase error. Originally, from 0 to pi, what was our value? What is the gain? What is the slope of the curve? Can you look at your figures and tell me? So this will be equal to VDD by pi, right? And then beyond pi, this gain will be equal to minus VDD by pi. So this was our original gain curve. So now what we have is gain is 0 for some time. Then it becomes equal to VDD by pi. Then again it is 0 for some time. Again it is 0 for some time. And then it goes to minus VDD by pi. So effectively, we have regions where the gain is now equal to 0. So if you have flat regions in your characteristic curve, we call them as dead zones. Because if your input is within this region and it is changing, your loop is not able to respond to it, because the output of your first block itself is not changing. It's a constant. Okay. All right. So again, I'll give you one quick question. You can do this as a homework. So plot VPD average versus phase error for XOR PD when the XOR supply is between minus VDD, is basically minus VDD and plus VDD. So till now we had waveforms that went from 0 to VDD. Now the XOR output is going to go from minus VDD to plus VDD. So you can see what change happens to the characteristics, and you can also calculate the KPD. Okay, so now let's move on to the next phase detector. Any questions so far? Why this is flat? Why we have a flat region here? Okay. So was the white curve clear when I plotted it here? Let me do that again. So this part is fine, right? Okay. So the average is now area under this curve divided by the time period, right? So now for the red curve, what has happened is I will have a small pulse here, right? And the width of this pulse is going to reduce. So that will become like this, right? So now I have to, if the area under the red curve is same as the area under the white curve, then the average is same, correct? So now if you think carefully, you'll see that how much ever width has come here, so much has basically reduced here, right? So area under this red curve is basically same as the area that you had earlier, which means the average is not changing. So now if I plot this VPD average, it will remain a constant. Okay, so you can find out till what point it is going to remain a constant. Do this analysis, see at what point onwards does the area begin to increase. Okay, is that clear? Okay, so now we move on to the SR latch based PD. So let me first sketch out an SR latch. Okay, so quickly tell me the truth table for NOR. 0, 0, 1, 1, 0, 1, 1, 0, and 1, 1, it will be 0. Okay, so basically, if I have 1 as one of the inputs, my output is immediately 0. So if I have 1 as one of the inputs, I don't even have to worry what the other input is. Okay, so let's now do the truth table for the latch. So I have S input, R input. I'm going to write Q and Q bar. So for this case, how would the output look like? Which is 1? Q is 1 or Q bar is 1? Q is 0. Why? But you're telling that from your memory, right? So R is 1. So one of the input to the NOR gate is 1. So I don't have to worry what the other thing is. Q becomes 0. Right? So similarly, and then this becomes 1. Similarly, for SR, this is 1 and this is 0. What happens when both of them are 1? So you're telling me invalid state because you're telling something from your memory. Just analyze this and tell me what that state is. Both are equal to 0. Does this state have a problem? Why is there a race condition? That decides the output. Okay. But other than that, this 1-1 state doesn't have a problem. The problem happens if you go from, so let's say this is 0, 0. If you go from 1, 1 to, if you go from 1, 1 to 0, 0, then you have a problem. If you move from 1, 1 to 1, 0 or to 0, 1, you are still fine. There is no race condition involved because the output is clearly defined. But if you are moving from 1, 1 to 0, 0, then depending upon whether S became 0 first or R became 0 first, you could have a very different output. Okay, is that clear? Okay, so now the problem is that this S becoming 0, R becoming 0, sometimes if both of them happen around the same time, right? Now it becomes a function of the noise and mismatches in the system. So if both of them happen roughly at the same time, then depending on which path has a larger delay, that is mismatches, or depending on which path is seeing a larger noise, your circuit could move to one of the states. Okay, and then it will get stuck there because what is the function of the 0, 0 position? Why is it holding? What do you mean by R and S are deactivated? Let's say Q bar is 1. So is that explanation clear? Right. So now this is going to hold the state. So if you move from 1, 1 to 0, 0, depending on which of them went 0 first, you might either end up in one of these states. And then as the other, so let's say set went to 0 first, so you move to 0, 1, right? So let's say you had S and R as 0, 0 initially, which means your output would be, S and R is equal to 1, 1 initially, which means your output was equal to 0, 0. Now, if S and R went to 1, 0 first, then what is your output? It will become 1, 0. Q bar becomes 1, 0. And then it goes to 0, 0. So you are basically moving from 1, 1 to 0, 0, but you have this intermediate state. So now the state that is getting held would be equal to 1, 0. Now, on the other hand, if instead it had 0, 1 as the intermediate stage, which means your output is also 0, 1. So now when you finally move to the 0, 0 state, your output is going to be 0, 1, right? And if they were happening very close to each other, depending on the race conditions present in the circuit, you could end up with either of them. And this might not even be a function of the input at that instant. It could be a function of the noise in your system. That is why when you deal with memories, we say this is the invalid state or a forbidden state. But for this circuit as such, you see that this is not causing a problem. We are going to analyze how this can be used as a rate detector. And you will see that this forbidden state is not really forbidden for us. Okay. Now, of course, with the naming convention I have followed, it looks like Q and Q bar are complements of each other. Again, this is not really necessary for us. So instead of calling it as Q and Q bar, I will call this as up and down. Okay. So there is no need to have a confusion when both of them are 0 because it's not exactly Q and Q bar for us. Is this fine? Okay. So we have to now plot in1, in2, up and down. And I can see that we have crossed the 6:30 time limit. So we'll do this in the next class. Okay.